Let's discuss titrations and buffering. And here's some learning objectives copied from the AP syllabus. This is a curve that was done by a student. pH is traced against the volume of sodium hydroxide added. We're titrating 0.01 molar hydrochloric, that's the blue line, and 0.01 molar acetic acid with 0.01 molar sodium hydroxide. So the equivalence point should be right at 25 milliliters of added sodium hydroxide, and you see that is very close to being true. You will notice that the pH of the hydrochloric acid titration starts off and remains below the pH of the acetic acid for the same volume of sodium hydroxide added. In the acid phase, the pH of the acetic is always higher than the hydrochloric. The pH break, as you can see this sharp turn upwards, is sharper in the hydrochloric than it is in the acetic acid titration. The pH at the equivalence point for the acetic acid is higher than for the hydrochloric, which of course should be at 7. And once the equivalence point has been passed, adding the sodium hydroxide produces the same trace in both of these reactions. Let's interpret that. Well, first of all, the pH before the sodium hydroxide is added is higher for the acetic acid because it is incompletely ionized, whereas hydrochloric is 100% ionized. It dissociates 100% because it's a strong electrolyte. The pH curve for hydrochloric acid is sharper because if you react a strong acid and base, there is no buffer produced. There is a buffer produced when you react a weak acid with a strong base. The equivalence point for the acetic acid is higher because when you react acetic acid with sodium hydroxide, you get acetate ion, and acetate ion hydrolyzes. That is, it reacts with the water, tugs a hydrogen ion in large numbers away from the water molecule, leaving hydroxide ion. The chloride will not react with water to form hydrogen chloride because that's 100% dissociated. And after the equivalence point, there's no acetic acid remaining, so there's no more buffer between the acetic acid and the acetate ion. Only sodium hydroxide then is around to affect the pH. Titrating weak acids with strong bases, or weak bases with strong acids, always produces ions that act with the remaining acid or base as a buffer, as something that resists pH change. So only when both acid and base are strong is the pH at the equivalence point equal to 7. That's something worth remembering. So hydrochloric and sodium hydroxide will react and give you an equivalence point at pH of 7. Any other conditions make you treat it as an equilibrium problem. And it's a stoichiometry problem with a limiting reactant being used up, and the excess, what's left over, is responsible for the strange pH. The general rule, of course, is strong acid and strong base, your pH's equivalence point is at 7. Strong acid and weak base, the pH is below 7. It's kind of like a tug of war favoring the stronger. A weak acid and a strong base gives you a pH above 7. Same philosophy. So it is important to estimate the equivalence pH and choose an indicator, acid-base indicator, with a pKa close to the equivalence pH. Now there's two words. Equivalence point, as you know, is the point at which the acid moles equal the base moles. And therefore we're reacting 100% acid to base to make water. The end point is the volume of titrant added where the indicator changes colors. And you want the end point and equivalence point pHs to be about the same, so that when the color change occurs, you know the equivalence point has just passed. So, if we titrate 50 milliliters of 0.2 molar nitric acid with 0.1 molar sodium hydroxide, we should be able to calculate the pH at various points based on the fact that the only thing that's produced is a pH 7 salt, and that'd be sodium nitrate, with, and of course the water is also produced. So you should be able to calculate the pH before you add any sodium hydroxide, and all you have is 0.2 molar nitric. After you add 10 milliliters of sodium hydroxide, then 20, 50, 100, and 200 milliliters. Here are the answers. The initial pH after adding 10 milliliters of sodium hydroxide, after 20 of sodium hydroxide, it's just edging up, after 50 of sodium hydroxide, after 100 of sodium hydroxide, again we have equivalence point, and then after 200 of sodium hydroxide, the pH jumps up to 12.6. You should have been able to do those. And here is the strong titration curve. So if you didn't have a pH meter, what indicator would you use in this titration where the equivalence point is at 7? And the answer is probably phenolphthalein. Now there's 5 points of interest in any titration curve. The first is the initial pH. The acid or base in the flask, you divide the number of millimoles by the total milliliters of total solution. If it's a weak acid or base, you'll probably need a rice table to find the hydrogen ion concentration using the Ka or Kb. Now, after you add some titrant with strong acid weak base or strong base weak acid, you have a buffer situation. And let's find the pH after you add some titrant. If it's strong, you're just subtracting the millimoles of base from the millimoles of acid, divide by the total volume, and then from that calculate the pH. But if you're going weak, strong, you're going to use, for a weak acid, the hydrogen ion concentration is equal to Ka times the ratio of acid divided by base. That's something worth memorizing. The next point of interest is the pH at the half equivalence point, the midpoint of the titration. You're halfway to the equivalence point. Therefore, the ratio of acid to base is 1. If you're titrating into acetic acid, you've got the same number of millimoles of acetic acid and acetate ion. And at this point, the hydrogen ion concentration is equal to K for that acid, because the acid and the base are the same. At the equivalence point, hydrogen ion and hydroxide ion concentrations are the same. Of course, if it's a strong acid, strong base, the pH is 7. But you calculate the pH of a hydrolyzing salt formed in the reaction, like say sodium acetate, you'll use a rice table with all the acid or base being neutralized. The only thing you have left is the hydrolyzing ion like acetate or the ammonium ion. Beyond the equivalence point, all you need to do is determine the excess acid or base millimoles and divide by the total milliliters. The buffer is out of the question. From that, you calculate the pH. There is no hydrolysis factor involved in this because either the acid is all gone or the base is all gone. So in practice, if 30 milliliters of 0.020 molar acetic acid is mixed with 15 milliliters of 0.020 molar sodium hydroxide, what's the pH of the mixture? Hint, this is halfway to the equivalence point, 30 milliliters of 0.02 against 15 milliliters of 0.02. Do you remember? A over B is 1, and therefore the hydrogen ion concentration is the same as Ka, 1.8 times 10 to the negative fifth. Plug that into your calculator and find the pH is 4.74. the other thing to remember is that you flip the equation upside down if you're working with a Kb, say an ammonium hydroxide and hydrochloric acid titration. You just turn it upside down and it's base over acid times Kb is equal to the hydrogen ion concentration.